Hi, everyone. Well, now we're ready for our last measurement, which is the measurement of the T2 time, or the true dephasing time. Remember the issue. Let's see, can you see that on the handout? After we excite the system with a pi/2 pulse, the signal will decay away rapidly. But this isn't real dephasing. This just has to do with the inhomogeneous magnetic field. If we do a trick, we can reverse that dephasing and recover the signal. Here's how it works. After the signal has decayed away, we can then go and apply a pi pulse. And what this does is it flips all of the spins by 180 degrees. As discussed in the handout, the spins that were now ahead because they were precessing faster will be behind, and the spins that were behind will be ahead. After they continue to evolve for an equal amount of time, then they should all rephase. They should come back together. And then we should get a second pulse called the spin echo. This is the time of the initial pulse, the pi/2 pulse. This is the time of the pi pulse. And then this is the time of the pulse echo, the spin echo. Notice that we didn't apply any signal, any excitation for this one. It happens all by itself. Here, let's look at the oscilloscope screen now. Right now, we have an A pulse, which I've adjusted to be a pi/2 pulse, okay? We have maximum signal, whoops. There we are. Now I'm going to turn on a B pulse. You can see it here a little bit. Oops, we lost triggering. Okay. Excuse me 1 second. Okay, we've recovered our trigger. So this is the A pulse. Here's the B pulse. Now if we make the B pulse longer, we're going to set it to be a pi pulse. We'll make it longer and longer, and then we'll minimize that here. So we have the A pulse, the B pulse, and look, here's a third pulse, which we didn't program. It just appeared spontaneously, and that's the spin echo. Pretty cool, okay? So now we can look at the height of the spin echo. Notice the time between the A pulse and the spin echo is much longer than the dephasing time. So we really are able to get around the dephasing due to the inhomogeneous magnetic field by playing this trick. Now what we're looking for is to see the true dephasing. That is, if we make this delay larger and larger, what we expect is that this pulse will get smaller because when we try to rephase the spins, not all of them can come back in phase because some have been altered by random processes that can't be reversed. And we can search for that now by just making the delay between the A pulse and the B pulse larger. Okay? So let's go to look for that. I'm going to reset the oscilloscope a little bit. There we are. Yes, let's do one more adjustment. And then now we could start making the time between the pulses larger and larger. Let's see, I think I'll make them a little larger. There we go. And then, well, there's a nicer way of doing this than just simply adjusting the delay. We can use multiple B pulses. Each one is a pi pulse, and each one should have the same effect. It should produce a spin echo, okay? So instead of one B pulse, we can have 2, or 3, or 4, okay? Now if we like, I'm gonna change the scale again. There we are, and move it over. We can continue to add pulses, 5, 6, 7, 8, 9, 10. Okay, here, let's do 20. All right. Finally, let's do some signal averaging so that we can overcome the fluctuations in the signal and get a nice clean result. So here's what you're seeing. You're seeing the A pulse, and then you're seeing a succession of spin echoes that come after B pulses. And what you can see is that as the delay gets larger and larger and larger, the amplitude of those spin echoes gets smaller and smaller and smaller. And that's due to true dephasing or homogeneous dephasing. Okay? Well, very good. So what I'm going to do now is we're going to stop this and capture this data, and I'm going to include it with the data packet that you'll get for this experiment. Okay, 1 second.